Okay, hello and welcome back to Biology 206. I'm Dr. Jennifer Baltzer, and today we're going to be having our final lecture of the term. And the topic of this lecture is global ecology. Now, the chapter, so chapter 25 that this is based on, it focuses on a few different aspects of global change. I'm really going to squarely focus on climate change. And so you only need to pay attention to the portions of the chapter that are focused on climate change and its impacts. Okay, so climate change. We've already talked about this a little bit during the course. You know, it has been a thread that has woven through the course in terms of thinking about climate warming impacts on different scales. But the definition of climate change is a significant directional trend in climate conditions lasting at least 3 decades, okay? So this is the definition of climate change from your text, and we just have to recall back to our discussion of weather versus climate, you know, these differences in kind of the temporal and spatial scales that those two terms relate to. And so these are global, so for the whole planet, global average surface temperatures. Okay, and so when we're thinking about temperature in most naturals, in the natural sciences, we think about long-term normals. And so, you know, if you measure the temperature of the planet or of the region over the course of 30 years, we'll often talk about 30-year normals, or in this case, it's 100 years. If you take that average temperature over that time period, it's the climate normal. And it can also be precipitation, it can be any climate variable. But we talk about those normals as, you know, okay, here's what the typical conditions over the course of this long time period look like, okay? And so what this graph represents is a change from that long-term average. And so in this case, it's the average between 1901 and 2000, so a 100-year time period. So the difference for each of these years from that average, okay? And so what we see is that in the late 1800s and early 1900s, the temperatures for every year were cooler than that long-term 1900 to 1901 to 2000 average temperature, okay? So a negative value means that the temperatures were cooler, and this is represented in blue bars. And a positive value means that the temperatures were warmer. And so we see that we get over here to the 1940s and we start to have, you know, this is where there are some periods less than 10 years that are a bit warmer, and then we have cooler years and warmer years and cooler years. And this is what we expect, temperature fluctuating around an average, right? But then we hit about, you know, the late 70s, and every year from the late 70s onward until today has been warmer than that 100-year average. And we see that this is a trend. It is going up. It's not as though it's a little bit warmer and staying stable. Every year it's warmer and warmer. And so in 2020, the global average surface temperature was 1 degree, nearly 1 degree warmer than that long-term average, okay? So this is a really clear representation of this process of climate change and what is happening to this planet. And so the Earth, as you can see from this, is experiencing significant climate change. And it's not just temperature that we're seeing change, there's patterns of precipitation that are changing, the frequency and intensity of different climate processes are changing. So there's a lot of components of the climate system that are changing in tandem, but a really important one is this warming signature. Okay, so as we see from this graph, the planet is warming rapidly, but one thing, you know, and you, when you look at this, you may say, oh, well, it's only 1 degree. 1 degree is not a lot. 1 degree at the whole planetary scale is a huge amount. But the other thing to keep in mind is that the planet is not warming evenly. This is a heat map of the temperature anomalies between 2017 and 2021 compared to the long-term average from 1950 to 2000 or 2010, I believe. And these portions of the, the highest latitude parts of the planet up here around, that Canada occupies, so boreal and Arctic regions in particular, have warmed most rapidly. We heard about this in the news here in Canada, that Canada was warming at a rate that was 2 or 3 times faster than the rest of the planet. This is because we are a high latitude nation. High latitude parts of the planet are warming much more rapidly. This is due to a whole range of processes, including the loss of ice and snow that changes the reflectance, the albedo of the surface of high latitudes, but also concentrating of carbon dioxide, atmospheric carbon dioxide in higher latitude regions. So we have parts of the planet that are warming much less, and parts of the planet that are warming much more rapidly. And so the places that I work in the north, for example, have warmed between, for the annual average, have warmed between 3 and 4 degrees Celsius. In the wintertime, some of these places have warmed between 10 and 12 degrees. And so, we're no longer talking about these values that may seem small to you. It's really dramatic increases that take us outside of, well outside of the long-term normals in those areas, and are having really rapid and substantial consequences for those parts of the planet. So there's a whole lot of consequences of this. I want to focus in on, what is driving this warming process, some of the consequences and feedbacks from a carbon perspective on the planet. That'll really be the focus of today, but we could spend a whole entire course on looking at how different components of climate change manifest themselves at the planetary scale or at regional scales. And certainly there are climate change courses in geography, and if this is something that you want to learn more about, I really strongly recommend you look into those opportunities, because there are so many different aspects of the natural world that are being dramatically modified by this rapid warming that the planet is experiencing. Okay, so we've already talked about this a little bit, but I want to dive a little bit more deeply into this, and this also links with guest lectures we've had that have talked about climate warming. But recent climate warming is driven by human emissions of greenhouse gases. This is unequivocal. There is no, scientists are absolutely certain of this. There is no uncertainty around this statement. We can see the patterns here of various greenhouse gases. So if you recall, the way climate warming works is that we have an atmosphere that is full of various gases. This atmosphere is really essential to life on the planet. It has allowed the planet to stay warm and support all the amazing life and biodiversity that we have on the planet. But as the concentration of those gases in the atmosphere change, this modifies how heat is captured within the biosphere of the planet. Okay, and so as we move through recent history, so from the year 0 to the year 2020 or 2000 here, what we see is fairly stable concentrations of carbon dioxide, nitrous oxide, methane, all greenhouse gases. And then we hit that same time period around the time where the planet started warming really rapidly from our previous figures, around the 1970s, 1980s, the Industrial Revolution, just after the Industrial Revolution. And we see this skyrocketing of all of these greenhouse gases, this exponential increase in greenhouse gas concentrations. And so with this increase, basically we've insulated the planet. So further, we've added more greenhouse gases to the atmosphere, and this traps heat just like a greenhouse does. This is why it's called the greenhouse effect. It traps heat just like a greenhouse does. And so heat being released from the surface of the planet is returned. It's maintained within the planetary boundaries. And so this is what's driving the warming of the planet. And there has been a lot of, you know, questioning of the validity of this statement in terms of whether or not humans are actually the drivers, because there's all kinds of natural processes that drive changes in climate, a warming and a cooling of the planet. But it's absolutely clear at this point. So scientists have modeled, and we've seen this in a previous lecture, scientists have modeled, looked at a variety of drivers, both human drivers, so greenhouse gas emissions, ozone emissions, land cover change, and aerosol emissions. These are all things that we are doing to modify the planet, to modify the atmosphere. So these are all incorporated into the red line of human drivers. Then there's natural drivers, and you may have heard about these. So volcanic activity, that's a really important component of, you know, planetary cooling. Solar changes in the solar cycle, where there's, you know, more energy reaching the planet's surface and less energy. So solar activity can be an important component of changes in climate through time. And then orbital components of how the Earth is changes in the orbiting of the Earth. Okay, so these are all natural drivers that have the potential to be changing the climate on the planet. But what is very clear when we run models that incorporate, so the black line on this graph is observed data. So here is our temperature difference from average, and this is in Fahrenheit, so this is an American figure, but you get the picture. An increase, a positive value is an increase in temperature, a negative value is a decrease in temperature. So this is the temperature difference from that long-term average, okay, that normal value, normal temperature value. And so from the 1880s right through to, you know, into the, we see this is the sort of the error associated with these models, right through to probably about the 60s or 70s, you know, there was variation in this black line, but it didn't really show a systematic increase or decrease with time. Once we hit about the 60s or 70s, we start to see this really dramatic increase in that black line where temperatures have rapidly increased. And we saw that in the previous figures. This is the same kind of data as we were seeing in that red and blue bar chart figure. Okay, so then we can model what we would expect temperature to look like, temperature changes to look like based on human factors only, based on natural factors only, or based on a combination of the two. And what you can see, so the blue line is natural drivers. What you can see is that, and the important point from this is where the black line matches up with the other lines. That's where the model fit is good. We're not expecting that every year we're going to predict perfectly, but where the trend in you know, modeled drivers fits the observed data, that's where we expect, that's where we know we have sort of captured what is, you know, what the drivers of this change actually are. And so the take home from this is the blue line here is our natural drivers. It doesn't track that black line at all. It did in the past, you know, all of these lines were sort of bumping around each other, not, you know, not tracking each other perfectly, but none of them deviating too far from zero change from the long-term average. But with natural drivers, we would have expected to stay right in around that zero change point. So the natural drivers have not changed enough to drive the rapid increase that we're seeing. In contrast, when you look at human drivers, which are depicted in red, their projected change follows almost perfectly that black line, or the combination when you combine all drivers, so human and natural. So this tells us that the human drivers are really the factors that are underlying the rapid increases in temperature we're seeing on the planet. Okay, so unequivocal support for this statement. Okay, and not only is temperature increasing rapidly, but temperature and carbon dioxide concentrations both increasing rapidly, but they're increasing beyond the scope of what we've seen over a very long time period. Here we have carbon dioxide concentrations in parts per million, reflected by the red line, and Antarctic temperature anomaly, reflected by the black line. So again, negative values mean lower than the long-term normal, positive values mean higher than the long-term normal over the last 800,000 years. And this graph is produced using ice cores collected in Antarctica. They do the same with ice cores collected in the Arctic. You can watch a little video about how this is done and what this looks like. It's really amazing science. They go and they core ice in these incredibly remote places, and then they measure, for CO2, they measure gas concentrations in bubbles trapped in the ice, and can look at what the atmosphere looked like at that point. For temperature anomalies, they use changes in stable isotopes. So you've got, in this case, 2 isotopes of oxygen, so one heavier isotope and one lighter isotope. If you want to read a little bit about isotope ecology, there's a nice box about it in chapter 5. But there's a heavier isotope and a lighter isotope, so O16 and O18, O16 being the lighter, O18 being the heavier. And depending on the temperature of the planet, the proportion, the ratio of O18 to O16 to O18 in ice cores and in sediment cores from the ocean vary in response to, the fact that, first of all, O16 evaporates more readily than O18, and so it gets carried up to the ice sheets. It gets evaporated into the atmosphere, then carried through circulation processes and deposited as snow on these ice caps. So during cool periods, the ocean will be enriched in O18 because O18 stays in the water better than O16, which is evaporated more readily, and then O16 gets locked up in the ice and snow that forms these masses of ice and snow during cool times, during these glacial periods. So what this is showing us is the glacial maxima and minima over the last almost million years. So here's the last glaciation, which was about 12 to 15,000 years before present. Okay, but during warm times, those ice caps, the snow and ice, melt, and that fresh water is released into the ocean, and it's enriched in O16. So then the ocean waters become enriched in O16. And so during these periods of warm temperatures, there will be a lot more O16 in the ocean water compared to O18. Okay, so they're able to use ice cores and sediments from the ocean to quantify these temperatures through time and relate them to paleo CO2 concentrations as well. So it's pretty amazing research, and it has shown us that this close relationship between temperature and CO2, which is really important for understanding the impacts of our own fossil fuel use on planetary temperatures, but also to show us what the range of variation has been over a much longer time period than our records, our measured records of the atmosphere allow. And this can be extended back even further. So here is the time period I was just showing you. So these are those glacial and interglacial periods. And remember, this is on a log scale. So this goes back to 1 million years, thousands of years BP, so 1,000 years. And it's on a log scale. So this is, this is 10,000 years ago when the ice sheets and the glaciers were retreating following the last glacial maximum. And so this is our current, for a long time, the climate was incredibly stable. And then it started to increase. And as you all know, we're well above 400 parts per million now. So we're into this exponential rise. What these different RCP values are, these are modeled projections based on our activities. So if we continue business as usual, just doing whatever we want to do and burning as much fossil fuels as as our hearts desire, this takes us up to a carbon dioxide concentration of 2,000 parts per million, which the planet has not seen since about 400 million years ago. Okay, so this is really not a place we want to go. This area, this time around here, it corresponds with the Carboniferous, when we had tropical forests all over it was a very wet, warm climate with tropical forests everywhere, basically a completely different climate system. It's a time where we had, temperate forests way up in what is now the Arctic, right? So this is a CO2 concentration that we haven't seen since 400 million years ago. And just a side note, these times prior to what we can get from the ice cores are quantified using fossil records, so stable isotope geochemistry in soils, so paleosols, stable isotopes in various foraminifera, so shelled organisms, information from liverworts and stomatal densities and fossil records. So there's a lot more uncertainty associated with this, and you can see this scatter, but regardless, what we had was a climate that was a lot higher in CO2 concentrations and a lot warmer as a consequence. So these different model projections, so this is if we really take strong action and strong, rapidly reduce our use of greenhouse gases and undertake a huge amount of kind of mitigation and adaptation, and we'll talk about that later in the presentation. So there's a whole range of scenarios, and this is what when you hear about predictions from, say, the Intergovernmental Panel on Climate Change, these are the kinds of projections that they're using based on different, business as usual or different mitigation scenarios, okay? So these are our potential futures in terms of greenhouse gases. We're currently, sitting above 400. What we want to do is start to bring that back down so the planet doesn't warm too rapidly. And we'll see, why that's so important in a moment. Okay, so in essence, we are disrupting the Earth's carbon balance, and we've already seen a figure similar to this in terms of, I believe we have, or maybe that was focused on radiation balance. Regardless, this is the sort of the carbon balance for the whole planet, and it shows where there are different carbon stocks. So we have a number of different carbon stocks, the atmosphere, and these numbers correspond to the quantity of carbon dioxide stored in those respective pools, or where it's not in a box, it's a flux, right? So we have atmospheric stocks, we have oceanic stocks, and so you can see the ocean stores a massive amount of CO2 compared to the atmosphere, for example. And there's surface ocean waters and there's deep ocean waters, and we have a lot more carbon dioxide stored in these deep ocean waters compared to surface waters. There's the land surface, and we see here the soils store 1,500, the vegetation stores 650, so a lot of storage on the planet compared to the atmosphere. And then there's sediments and rocks, which are, very stable forms of carbon, very much locked away. So the really dynamic components of the system are these atmosphere and ocean fluxes, and you can see that the amount leaving the ocean is roughly equivalent to the amount entering the ocean. This is, carbon dioxide diffusing into the ocean and being released from the ocean. So it's going to be in balance, but we do know that the amount and that we're seeing, because of the atmospheric carbon dioxide concentrations increasing more, these fluxes are getting larger. We have more CO2 entering the ocean system and acidifying those waters. The other component, of course, is gross primary productivity, so how much carbon dioxide is taken up by plants, by vegetation, through autotrophic processes, through photosynthesis, and how much is lost from the system via respiration, both metabolic respiration, through metabolic respiration processes, I should say. Okay, so, prior to, this would be in, for a very long time, these GPP and respiration rates were pretty much in sync. You have about the same amount coming into the system as you have leaving the system, and that's, it's in an equilibrium, I guess. And what we are seeing now is that the amount of CO2, so if you ignore these pieces, GPP is approximately equivalent to respiration. But the problem is that we have these other pieces that are now being driven by humans. So fossil fuel use and land use change. And those are leading to fluxes that are leaving the surface of the planet that are much, much higher than what the planet is able to take up. And this gets exacerbated when you start to modify land surfaces so substantially that this GPP starts to decrease at the planetary scale. When large areas are deforested, for example. So where we have the real imbalance in terms of increasing carbon dioxide concentrations comes from this terrestrial component and human activities in the terrestrial environment. So fossil fuel use and land use change. Okay, so just to kind of touch on this component a little bit more as well, there are some really important, and a few of you did your Minute Ecology videos on ocean processes, and so a number of you know about kind of some of the biological pumps and the mixing of CO2 from surface ocean waters where we have less CO2 but more productivity, and then contributions of CO2 from less carbon storage but greater productivity, contributions of carbon from these surface waters to these deep ocean waters, which is a really important part of kind of carbon sequestration on the planet. Having these surface waters fixing CO2 via photosynthetic processes, those organisms are consumed by other organisms through food webs, and then eventually, detritus and various biologic pumps that are associated with different organisms, including whales, lead to a massive amount of storage of carbon in the deep oceans. Upwelling and downwelling processes are really important in ocean carbon dynamics as well, with downwelling leading to a lot of carbon moving from surface waters to deeper waters as well. Another important component is sinking of, we know that in the oceans there's a lot of carbon that's locked up in the shells of organisms. So a lot of marine organisms have carbonate in their shells, and that's carbon. And so as those organisms die, their shells sink to deeper layers, and the carbon in those shells ends up being locked away and kind of lost in these deep ocean layers. So there's a number of processes that lead to this difference between the surface ocean water carbon stocks and the deep ocean water carbon stocks, but the oceans are a really critical reservoir of carbon on the planet. Okay, I just want to check that I didn't want to say anything else here. Yeah. Okay. So then thinking about, some of the implications of increasing atmospheric carbon dioxide concentrations, very early on, as carbon dioxide concentrations were increasing on the planet, there was the expectation, at least for terrestrial ecosystems, that increasing carbon dioxide concentrations in the atmosphere would enhance terrestrial productivity, and this might offset some substantial portion of our emissions. And this was sort of a hopeful view on the potential for nature to kind of clean up our mess. So there were some reasons for this, is that, we know that photorespiration is a really big problem for, particularly for C3 plants, which are the majority of the diversity of the planet. So photorespiration, where oxygen is fixed instead of carbon dioxide, making the whole cycle really inefficient. And so by increasing carbon dioxide concentrations in the atmosphere, you reduce those photorespiratory costs. it also allows for improved water use efficiency. If there's higher atmospheric carbon dioxide concentrations, stomates don't need to be open as often or as much, and so this leads to reduced water loss. So you can still fix the same amount of carbon but lose less water, which improves your productivity, reduces the water use in the system. There's all kinds of benefits to the plant for this. And that this increased CO2 fixation, improved water use efficiency would all lead to enhanced growth, enhanced carbon capture in these ecosystems, okay? And so offsetting some of our additional emissions, that the idea was that this sink would increase, this GPP uptake would increase, and that would take care of some of these emissions associated with fossil fuel use in particular, but increasingly land use change. And so one of the things, and I highlight this because it's in your text and you might be wondering what these funny circles in the forest are, one of the ways that scientists took a look at this is through some large-scale experiments that happened in ecosystems around the planet called the Free Air Carbon Dioxide Enrichment Studies, or FACE. So when you hear about FACE experiments, it's free air carbon dioxide enrichment. And what they did, you can see these are all replicated units across a landscape. So this is some sort of plantation forest here, given the regularity of it. Well, what they did was set up these big towers in circles around patches in forests, in croplands, a whole lot of different ecosystems, natural grasslands, any number of ecosystems, and they basically pumped CO2 into these areas. And so lots of CO2 leaked away from it, but basically it elevated the carbon dioxide concentrations within these circular areas, and you can see the impact of that. So this is an infrared image from one of the crop FACE experiments. And so here's your ambient CO2 treatment and your elevated CO2 treatment, and you can see that the elevated CO2 treatment is about 1.5 degrees Celsius warmer than the ambient CO2 treatment. And so we can see that the efficacy of these CO2 enrichments. And so what researchers did in these experiments worldwide was, measure aspects of photosynthetic uptake, of, primary productivity, of growth, of biomass production, all of these things to evaluate what the implications of increasing atmospheric CO2 concentrations were. And, by and large, what they saw was pretty positive responses. So this is a review across all of the FACE studies that had happened up until, I think this paper was published in 2005, and they looked at a whole range of things. So these are C3 and C4 photosynthetic pathways. So we know about those photosynthetic pathways, we've talked about that. And what this is showing us, is showing us a number of measures. So saturated photosynthesis, two different measures of photosynthesis here. So our CO2 uptake, stomatal conductance, how wide open are the stomates? And we'd expect them to be closed more because the carbon dioxide concentrations are higher, and this is a measure of water use efficiency here. Okay, so it's a instantaneous transpirational efficiency. Okay, so what the x-axis is showing us is the percent change in elevated CO2. So in every experiment they had elevated CO2 and ambient. So what this is a measure of how different was the elevated CO2 from the ambient, or the just normal untreated. And so a positive value means it increased in response to the control. A negative value means it decreased in response to the control. And so what we can see is, and this is what they expected, increased photosynthetic rates in response to elevated CO2 concentrations, decreased stomatal conductance, meaning decreased water loss, and improved transpirational efficiency in response to elevated CO2 concentrations. And also, if we look at any of these growth metrics, so height, stem diameter, so how large around is the tree, number of branches, number of leaves, leaf area index, all of these things are measures, crop yield, measures of how much biomass is being produced by these plants, by these trees, and we can see that all of these things increased in response to elevated CO2. So this was, suggestive of a CO2 fertilization. So a positive growth response, you think about, you fertilize your plants with nutrients. If you have plants in your home, you'll add little fertilizer pellets to add nutrients to the soil. So that's fertilization. Well, this increase in CO2 concentrations in the atmosphere, it's referred to, when plants respond positively, is referred to as CO2 fertilization. But when we take a look at the whole planet using satellite imagery and using spectral indices that give us an indication of the primary productivity of the system, what we are seeing, and so this is a funny little, basically the ratio of gross primary productivity, so how much CO2 is taken up by the system, to atmospheric CO2. So we'd expect, if we were seeing carbon dioxide fertilization, that we'd see an increase in gross primary productivity with increasing atmospheric carbon dioxide concentrations. But in fact, through time, and we have satellites going back to 1982, that measured the spectral reflectance properties that allow us to calculate gross primary productivity, we see this consistent downward trend at the global scale. And if you look between two time periods, so 1982 to 1996 versus 2000 to 2015, we see this downward shift, a lower value in the later time period, suggesting that the efficiency or the response to elevated CO2 is decreasing through time. And the idea is that probably this has to do with other things becoming limiting, so soil nutrients, water availability, that there are other resources that plants need that have become limiting, not allowing them to respond positively to this enhanced CO2 concentration. So the take home of this is that yes, we do see CO2 fertilization in some cases, but at the planetary level, there does not seem to be that signature, or that the strength of that response is declining through time, and we think that is in response to increasing shortages of other important resources. Okay, so the long and the short of it is that probably these natural systems are not going to compensate for our emissions. We can't count on that. And the other component of things is that regardless of what productivity is doing, there are other changes afoot, okay? So warming is happening incredibly fast. Even if plants are able to increase their productivity somewhat, there are other factors that are changing at a pace that kind of outstrips those modest increases in productivity. An important one has to do with, the soil stocks. So if you recall the stocks of carbon in different parts of the terrestrial environment, the biggest carbon stock in the terrestrial environment was the soils. And this is especially true in northern ecosystems where we have these really carbon-rich soils that are frozen, so permafrost soils. And this is showing us a picture of massive ice wedges in soils beneath a sparsely forested system. These soils are incredibly rich in carbon and store a huge amount of our these permafrost soils store a massive amount of the terrestrial soil carbon stocks. In fact, if you look at it, so soils and vegetation together, they make up 2,300 teragrams of carbon. Permafrost soils make up 1,600, right? 1,600 of that total. So we have a huge amount of carbon locked up in permafrost soils, twice that of what we have in the atmosphere, right? So when we think about this, these have been very stable systems for a very long period of time. You've got this frozen layer of soils that has locked away carbon for, hundreds to thousands of years, right? So it's carbon that the atmosphere hasn't seen for a very, very long period of time. But we have global temperatures rising because of increases in greenhouse gas emissions from human activities. As temperatures rise, so warmer temperatures, you're thinking about these very cold soils. Not surprisingly, warmer temperatures means permafrost thaw. Okay, so then that previously inaccessible carbon in the soil that had been frozen and locked away now becomes accessible for different processes, including both aerobic and anaerobic respiration. Okay, so permafrost starts to thaw. Previously frozen organic material decays because it's thawing. This decayed matter releases CO2 and methane into the atmosphere. The CO2 and methane increase in the atmosphere because of this release from this massive pool of carbon in permafrost soils, feeding back to global temperatures. Okay, so there's this really wicked positive feedback where increasing temperatures lead to increasing thaw, leads to increasing CO2 release, which feeds back to accelerating climate warming further. Some of these feedbacks that we see in the climate system are really big problems and are already in motion, right? And so this is different ways that this can happen. So here's a diagram of an Arctic environment. You've got terrestrial environments where photosynthesis is happening and aerobic respiration, so our typical respiration photosynthesis balance. But then you have thawing permafrost and anaerobic respiration leading to the release of CO2 and CH4, as well as leaching of carbon from these terrestrial environments into aquatic environments that then leads to various loss of carbon from the system that way. So we have a really big problem in these permafrost environments, and really the solution, we really need these permafrost soils to maintain their carbon stocks. We need these to be maintained in an intact state, and really the solution to this is curbing our reliance on greenhouse gases and reducing climate warming as stabilizing climate warming as much as we can. So minimizing where we get to on those different model pathways that we saw. And this, only by doing that can we hope to keep some of this carbon in the ground. And so we really need to focus on action and reducing our reliance on fossil fuels and taking actions that help to mitigate increases in atmospheric CO2 concentrations and thereby mitigate temperature increases. Okay, and to give another example of a really important feedback loop that we see in the climate system, it relates to fire, and we heard a lot about fire in our Meet the Scientist session last week, and the impact of fire globally, and the increasing, the rise in bad fire, the rise in these large mega fires. Part of that is because of climate change. So rising temperatures create drier conditions in these fire-prone ecosystems and forests. They lead to milder winters with shallower snowpack. Shallower snowpack means less moisture in the soils in the following spring. Higher pest populations, and we heard about that last week as well, where you have a high pest load and it leads to forest tree mortality in forests and a greater flammability of that system, and longer fire seasons. So as the winters shorten and the summers lengthen, this leads to a longer fire season. So all of those things associated with increasing temperature are leading to larger areas burned from fires. We have basically a more flammable system because it's drier, so that leads to larger areas burned. When you burn more areas, there's more CO2 released to the atmosphere. So we have larger areas burned, more areas burning at the planetary scale, more CO2 being released into the atmosphere. Of course, that CO2 being released into the atmosphere in these big pulses, it increases atmospheric carbon dioxide concentrations, which then feeds back positively to global temperature increases. And so these, and we can see here's, modeled data across the last, 40 years showing what wildfire frequency would have looked like without and with climate change. And there's a huge impact, a huge signal of climate warming on the area burned, the severity of fires, the frequency of fires, all of these things. These are all components that we're expecting to increase with ongoing climate warming. So we have these challenges that, we really need to start to slow these processes down, because there are some important feedbacks that, again, even if productivity of vegetation increases somewhat, some of these feedbacks will overwhelm those signatures. And so this is really something we have to keep in mind as we're thinking about this climate emergency that we face and how rapidly we need to respond to that and take action. Okay, and we've already talked about oceans being a massive carbon sink. This is kind of a neat piece in the conversation that talks about some of these different pumps, some of these different carbon pumps in the ocean that lead to a massive amount of deep ocean carbon, and the important role of biodiversity in the oceans in terms of maintaining the ability for oceans to store a lot of carbon. Okay, so I'm not going to get into these, but basically we have these ocean systems that have had a diversity of organisms that help to promote carbon storage in the system, and are really incredibly important for buffering atmospheric carbon dioxide concentrations. Part of the reason that the atmospheric carbon dioxide concentration increases haven't been faster is because the oceans have been absorbing a huge amount of the carbon dioxide that we as humans have emitted. This has led to some pretty serious problems in the oceans, and some of you researched this for your Minute Ecology videos. In very simple terms, oceans absorb carbon dioxide from the atmosphere and create carbonic acid in the water. So you have carbon dioxide coming in, mixes with water, so carbon dioxide dissolves in water, and you have carbonic acid formed. The more carbon dioxide you have entering the ocean, the more carbonic acid, the more acidic the ocean is. Now, why is this a problem? Well, think about the organisms that are in the ocean. These are little shells produced by carbonate, and we know that if you pour an acid onto carbonate, it will dissolve the shell. So immediately that's a problem from a biodiversity perspective. But it also means that the formation of these shells doesn't happen as readily because this carbonic acid steals carbonate from the ocean and produces bicarbonate. Okay, so then that carbonate is not accessible to all of these various organisms that rely on it for production of these protective structures, their exoskeletons, etc. Including coral, clams, urchins, mussels, any number of marine organisms have these hard carbonate-based structures that allow them to live. Okay, so what we see through time, so again, here we have year from 1985 to 2015, and here we have pH, and this is measured at 3 different stations in the ocean: Atlantic Station 1 in blue, Atlantic Station 2 in red, and a Pacific Station in orange. And we see the same trend across all of these, okay? Again, there's variability in the pH in the ocean, but what we see is that the pH has been consistently decreasing over this fairly short time period from 1985 to 2010. Okay, and with continued increases in CO2 concentrations, the expectation is that pH will continue to drop. Now, why does that matter? Again, if we think about calcification, we see this really rapid drop in calcification rates after calcification, which is important for shell production, in calcification rates after about the mid-1980s, and we see this decline in pH that goes hand in hand with that. And if we look at either populations or species diversity of organisms that rely on calcification, on carbonate, calcium carbonate to produce shells, we see that at low pHs, their population and their species diversity is 0. And that as you reach this, pH of 8 and above, we see this exponential increase in both the number of individuals and the species diversity measured as the Shannon index. And so moving down from 8 down toward 7, there's a huge drop in the diversity and the biomass of those organisms. And so this ocean acidification associated with increased CO2 concentrations in the atmosphere has massive ramifications for ocean diversity, as well as the carbon storage of the oceans, because we know that, the sinking of these little shells to the ocean bottom plays a really big role in carbon storage. Okay, so some other things to think about when we're contemplating these increasing temperatures is species distributional shifts. And so this is a graph from your text. It's looking at alpine environments, and so we have elevation here, elevation of the summit, so the peak, from 2,800 to 3,500, and species richness. And so what this is showing us is present species richness and historical species richness. So what you can see is that at every single elevation across the board, we've seen, at every single sort of mountaintop, we've seen an increase in species richness. And this is larger at these higher elevation, at these lower elevation sites. And it's smaller still at these higher elevation sites where the climate is still cooler. But what we see is that this is a shift from here to here, here to here. So you can see species richness from one time point to the next increasing. What this has been attributed to is species moving up the mountain. So species distributional shifts in response to climate warming, leading to species moving from lower elevation places where there's greater species richness to higher elevation places where there has been less species richness. And this is driving this increase in species richness at high elevations. And you might say, well, that's great. They're fine then. We maintain biodiversity. But if you think about it, these are alpine environments. You can only go so high before you fall off the top of the mountain. And this is a real concern in a lot of alpine places where we're seeing these lower elevation species moving up the mountain in response to climate warming, that eventually they're not going to have anywhere to run, okay? So big concern there. And at the larger geographic scale, we've already seen this figure in our last lecture, but the idea of larger scale species range shifts along broad geographic, so latitudinal ranges, and questions about the ability of species to move in response to the rapidity of climate change that we are seeing. So this is a map of the distributional changes in response to the last deglaciation. So 18,000 years ago, ice was covering this much of the continent. By 12,000 years, it was here. 9,000 years, it had all, shifted northward further, and now we just have these kind of remnant patches of glacial ice. What we see here is that species distributions have shifted in response to those massive climate changes, but that's over the span of 18,000 years. We're talking about a time frame of, a century. 100 years, and we're seeing climate changes that species simply will not be able to keep pace with. So this is again a real concern. In montane environments where species don't have to move as far to move up, you move up the mountain and you change your climate quite dramatically. Species having to shift across latitudinal gradients will be faced with much more challenging endeavors, because they have to move much larger distances to really see a change in the climate. And so whether species will be able to keep pace with rapid climate warming, whether the landscape is intact enough, as we talked about in the last session, to allow species to move in response to these changes. These are all big concerns we have. Okay, so that was a lot of doom and gloom, and I just want to before we end that, I want to just drive home this point of the widespread impacts of climate change. I've given a few examples. We've heard examples throughout the term. These figures and the next few figures we're going to see are all taken from the most recent report from the Intergovernmental Panel on Climate Change, the IPCC. You would have heard about the IPCC in the news. It's the Intergovernmental Panel on Climate Change. And these are the world's leading experts on climate change impacts for all kinds of different things. And from impacts on ecosystems, which we see here, to impacts on various aspects of human societies. Okay, so these are not disconnected pieces. So when we think about, what I guess as, my experience seeing, IPCC report after IPCC report is that in the early IPCC reports, there was very little, what you see here on these colors is confidence and attribution to climate change. How confident are we that the change that we're seeing is attributable to climate change? Dark blue is high or very high, purple is medium, gray is low, white is evidence limited or insufficient. In the early IPCC reports, we didn't have a lot of confidence in the attribution of changes we were seeing to climate change. Now what you can see is that for every ecosystem, terrestrial, freshwater, ocean, whether it's species range shifts, whether it's timing and phenology, changes in ecosystem structure, whatever continent, whatever biome, most of those points are dark blue, that meaning that we have high or very high confidence that the changes we're seeing in those systems can be attributed to climate change. This should be alarming, okay? And likewise, when we look at human systems, we can look at negative adverse impacts or places where there could be positive or negative impacts. And again, what we see across the board is very high confidence that we're seeing negative impacts that are attributable to climate change with very high or high confidence. Okay, so lots of dark blue circles with negative values, whether you're talking about agricultural or fishery production, whether you're talking about displacement or mental health, whether you're talking about catastrophic events, all of these things, we can point the finger directly at climate change and human-caused climate change. So we really need to take action because we're having these massive impacts. The experts, the leading global experts, are confident that these changes we're seeing can be linked with climate warming. Okay. So to try to leave this on a more positive note, the other really nice thing about the most recent IPCC report was the focus on adaptation and mitigation and really, I guess, hopeful solutions to this really hard problem that we find ourselves facing. One thing I really want to drive home in this course, we have really focused on ecosystems and to some extent the climate system. But the reality is that we have these coupled climate systems, ecosystems, and human societies. They are not isolated. No matter what we think, we are not isolated from nature. Activities that we partake in impact the environment, impact the climate, and we are impacted by both of those components of the biosphere. Okay? And so when we think about what's happening right now, we have human society that's, degrading natural ecosystems. We're leading to habitat loss, habitat fragmentation, massive changes to the way the extent and functionality of these ecosystems. So really big negative impacts by human society on ecosystems. Big greenhouse gas emissions that are driving climate change. Then climate change has these impacts that we saw in the previous slide on both human society and ecosystems, and those impacts are large and by for the most part negative. Okay? So this is where we currently are, and this is where we need to be. We need to be in a place where we, as a human society, work on eliminating greenhouse gas emissions or reducing them as much as humanly possible, working to conserve and restore ecosystems so that those ecosystems can be resilient to climate change, to ongoing changes that we will experience, and so that they can continue to provision livelihoods and ecosystem services to us. We rely very heavily on these ecosystems for these provisioning ecosystem services. And so really, the most recent IPCC report was a call to this hopeful future where we work to, restore our natural systems, reduce or eliminate greenhouse gas emissions, thereby allowing, supporting ecosystem health, supporting planetary health, supporting human health and well-being and equity and justice and all of these things that we as people want to see happening. So the idea of climate resilient development that allows sustainable development that is resilient to ongoing climate changes, that will support ecosystems that will be able to handle, function effectively in the face of ongoing climate change that we will continue to see for some time, even if we stopped all CO2 emissions. So this is a really important thing to think about. You know, this is where we want to be. This is where we are now. This is a really dangerous path that we're on. And just a little case study to highlight how effective this can be and how it's already underway. And so it really, you know, there's lots of hope that we can use human ingenuity and rely on nature to support improved conditions for people worldwide, improved livelihoods, while also moving toward greater climate and planetary health. So, major issue in Ethiopia is aridity. So there's been a huge amount of drought, and this is a big issue in many parts of the world, is that climate warming and drying is leading to increased aridity, drought, and really big problems that way. And when precipitation does come, it comes in flashier amounts, so large amounts that you end up with a lot of runoff, a lot of erosion, all kinds of problems like this. All of these locations are places where different conservation, different restoration activities have been undertaken in the landscape to try to evaluate biologic, conservation, agriculture, exclosure, different managements, different restoration tools that can help to support improved water status in this environment. So different ways this is being done. Here we have various water interception. So basically, you know, terraces that intercept water as it's moving down slopes, slow it, allow it to infiltrate into the soil better. Here we have various vegetation barriers that slow the movement of water on the landscape. Reforestation, a really effective tool for improving water retention in systems, slowing water movement across the landscape compared to this denuded surface that we see in so many parts of the world. And the implication is this, that these communities have seen this is natural, healthy base flow in a regreened area. They've seen improved groundwater conditions, improved base flow, improved an improved hydrologic system. And so this I really feel like characterizes the kinds of things that we need to be thinking about in the context of this, you know, climate resilient development. You know, we have low rainfall and high evapotranspiration in Ethiopia that was leading to all of these negative conditions. So agricultural drought, low soil moisture and plant water stress, low discharge and water level in rivers and reservoirs, so insufficient water availability, decreasing inputs of surface water to groundwater, so groundwater tables decreasing. And this had really big negative impacts on communities, on people living in these areas, because the ecosystems were not functioning the way they should. When they implemented some of these restoration efforts, what it led to was decreased water loss, decreased runoff, a decrease in the runoff coefficient, so the precipitation to runoff ratio, an increase in the soil moisture, increase in groundwater levels, and a decrease in the flow from these systems. Okay, so what this led to is a reduction in agricultural drought and a reduction in hydrological drought, a reduction in socioeconomic drought. So the impacts of drought in those natural and human systems were reduced because of these activities. Okay? These activities also lead to improvement in regional weather conditions. When you have more evapotranspiration to the environment, because you've got better water status, more vegetation, this leads to, you know, the potential for more precipitation, so improved weather conditions. So there's feedbacks to the atmosphere as well, and by and large, you know, the microclimate becomes more desirable for all of these things, and then there's a lot of both positive human outcomes as well as environmental outcomes. And this is exactly what we want to see happening here. Using these conservation and restoration approaches to make these ecosystems more resilient to future climate conditions that may be hard to deal with, that then allow for human systems to be supported. Okay? So this is I guess my call for hopefulness is that we have lots of, you know, fairly low tech and also lots of high tech ways of slowing and in some cases reversing damage that has been done, and we really need to be actively taking a role in this. So just to end this, this shows us our past conditions and the various trajectories that those modeled emission scenarios could take us to. On the one hand, if we allow continued use of greenhouse gases, business as usual, everyone doing what they want to do, we're on a very kind of terrifying pathway where there's a lot of risk associated with warming. There will be a lot of poverty, a lot of ecosystem degradation, enhanced inequity and injustice, high global warming levels and high risk. Okay? In contrast, if we're able to take some of these approaches that allow us to improve the resilience of human societies and ecosystems, reduce our inputs to the atmosphere, thereby stabilizing the climate system, we can move along one of these pathways that takes us to much more just and fair and safe outcomes, where we have reduced poverty, ecosystem health, lower global warming levels, lower risk. And these are all associated with things like sustainable development actions, adaptation, mitigation, system transitions, okay? This shows us the opportunities we've missed by not taking action sooner. What we don't want to do is keep not taking action and miss our chance to take this pathway. And so this is just my plea to all of you to really think about this and think about where you can contribute to to making this change happen. And on that note, just as a final note, I do want to say what a pleasure it has been working with you and learning from you. And I hope you have learned throughout the course of this semester about various ecological issues and the world around you. But I do, just because of the topics that we've been covering, I do want to highlight that there are a lot of people who are really thinking about hope in the midst of this climate crisis that we're in, and how to take positive action, how not to look at this as a total doomsday scenario, but instead think about ways we can contribute to those sustainable outcomes that we all want to see happen. And a great example of this is Dr. Catherine Hayhoe. She's a Canadian. She lives in the US though, down in Texas. She's an atmospheric scientist, and she, if you Google her, you'll find all kinds of amazing TED Talks and different lectures where she talks about climate change and and really hope in the face of climate change. And I just wanted to flag that the University of Waterloo is actually hosting her on April 27th at 10 a.m. It's a virtual seminar, but I really think that any of you who are feeling, any level of, climate anxiety, or who want to hear about ways to take a more positive approach to supporting, climate action, she's a wonderful person to listen to, has really insightful, amazing ideas, and I would encourage you to register for the free seminar and listen to some of her thoughts. And with that, I am going to say farewell. I will see you this evening at student hours, and again on Thursday for our final Meet the Scientist session, where we will hear about another really important topic, which is decolonization in the natural sciences. And yeah, have a great day.